Guys, welcome back. So today we're going to be doing a breakdown of another section bank passage. Okay, so we're going to be doing one we haven't done before. So I did this one, this one I did not do. So we'll do this one right now. Okay, I've not seen this passage before. This is a live breakdown. I'm going to show you guys exactly how to, read the passage, where to highlight, how to pick the best answer choice, all that stuff. Okay, so if you guys are interested in tutoring, okay, I'm going to plug this in right now and then I'll get to the breakdown. All right, if you guys are interested in tutoring, all right, I made this group chat here. This is called MCAT 1% Accelerator. All right, so you literally, everything you need for the MCAT, I put it in this Discord here. Okay, so like I put in the old MCAT exams. I'm going to be updating that. MCAT wins. If you get a score increase in your MCAT, you can post it in here. This is going to be, right now, there's only 6 people in this Discord. Okay, this is going to be packed. It's going to be a lot of people in this, all right? Because I'm going to post a link to join in the description. So in here you get, what is this? The old MCAT exams, MCAT wins, group study sessions. You can meet up with people, study online. It's a community here for really high achiever pre-meds, okay? Because something that I had when I was studying in my MCAT journey is I had like 1 or 2 friends who were really smart and who pushed me, okay? So that's what I kind of want to create here. So master of content here, any questions you have will be answered in any of the subjects. All right, here you can tag me, ask me any question you guys need help on. Here you have breakdown passages for every section of the MCAT. All right, so this is pretty cool stuff, guys. The first 40 people I will let in free. Okay, the first 40 people, you don't have to pay for this. It's going to be a subscription. After that, it's going to be like $25 per month. Okay, so make sure you guys click on the link and get into this now before I start charging people to join this. All right, so that's what I have for you guys. But anyways, let's get into breakdown right now. All right, so as always, guys, go ahead and read the passage first and answer the questions first, and then hear me break it down. Okay, this is a section bank passage. All right, so this is a spoiler here. All right, so after your content review, then you can go ahead and look at this video. All right, and after, this is just help you guys out. All right, so this is question 1. This is question 2. All right, make sure you guys write down your answers, see which ones you got right and where you messed up on. All right. Okay, cool. I think that's it. All right, yeah, that's it. All right, write down your answer choices and then resume this video. Okay, passage 3. Human immunodeficiency virus type 1, HIV integrase, is a viral enzyme that mediates the integration of viral DNA into the host chromosome. All right, first sentence here, cool, basic content review. You should know this stuff, all right? Also, the way I'm reading this is the pace that you guys should be going at, okay? Notice I don't speed through this, and notice I don't be a fucking slowpoke, all right? In integrase is a 288 residue protein composed of 3 domains: the N-terminal domain, the catalytic core domain, and the C-terminal domain. The CCD contains 3 highly conserved residues: D64, D116, and E152. And mutation of any of these 3 residues abolishes inactivity. All right. Whenever they say conserved, that just means that in every integrase protein, you're going to see similar D64, D116. You're going to see those similar amino acids at those spots. All right, so first paragraph, nothing to highlight really. All pretty basic stuff here. They're just telling me about integrase. All right, so it's going to get complicated soon. I already know it is. All right, so integration of viral DNA into the host chromosome proceeds by 2 well-characterized steps. All right, whenever they tell you something that's going to happen, and there's like a comma here, pay attention, because they're going to try to make it complicated for you. That's how the MCAT is, all right? So 2 well-characterized steps, both of which are catalyzed by which is our integrase. In the host cell cytoplasm, each end of a newly synthesized viral DNA segment is bound at a specific long terminal repeat nucleotide sequence by 1 N dimer. Okay, so I'm going to highlight this here. Where do I highlight? Here. Okay. Upon binding, catalyzes cleavage of a GT dinucleotide from each 3' viral DNA terminus. Important here. Cleavage, each 3' DNA terminus. All right. Whenever I see cleavage, whenever I see bonds being broken or whatever, they mention that. Okay, I'm always highlighting it because it's pretty easy to test, about bond breaking, bond formation. They always test about that, so I'm always highlighting that. Still bound to either end of the viral DNA segment, the N dimers join to form a tetramer, which then binds host cell protein LEDGF at the CCD. All right, I hope you guys got that one. All right, so what's happening here is that the N dimers, they join, form a tetramer, that binds LEDGF. LEDGF is a host cell protein, okay? That is us. We have LEDGF. This virus, okay, it forms that dimer, forms a tetramer, binds our protein, and now this goes to the nucleus and it incorporates into DNA. All right. Then N catalyzes the insertion of the viral DNA into the host genome. All right. Not too complicated, but I could see how some people get tripped up by, these words here. All right, but it's pretty simple, guys. MCAT is easy. MCAT is always easy. Small molecule N inhibitors show promise as antiviral drugs against HIV-1. One class of these inhibitors are ledgens. All right, I'm going to highlight ledgens. What do ledgens do? Which bind integrase and shift its oligomerization equilibrium toward an inactive tetramer that cannot bind DNA. That's what it's doing here. All right, if we have an inactive tetramer not binding DNA, no integrase activity. Another class of small molecule inhibitors are short-length oligodeoxynucleotides, ODNs, whose sequences mimic LTRs. ODNs are competitive inhibitors for viral DNA for binding to N. And I'm going to highlight this because this is content review. I know this. Okay, I've seen competitive inhibition before. And so they might ask a question about it. This struck out at me. They didn't have to say this. They were just like, hey, they're competitive inhibitors. All right, this struck out at me, so I highlight that. Anything that strikes out at you, you highlight it. So pretty simple passage, guys. No figures we have to interpret here, okay? Very simple. All right, we have HIV. Okay, they're telling us about the integrase enzyme, how it works to incorporate into host cell DNA. All right, what's going to happen here is that we're going to bind, we have these viral DNA segments, the LTRs, all right, and then it cleaves the GT dinucleotide from 3', and then that is going to form that tetramer, binds to LEDGF, it gets incorporated into our host cell genome, all right. Nothing too crazy, very easy, guys. I keep telling you guys the MCAT is easy, but you guys don't seem to believe me. All right, so let's go ahead. What bond is cleaved by N during the first reaction of integration? I think the first one was the cleavage of GT. So it's okay if you double check in the passage, just make sure you do it quick, all right? Upon binding, N catalyzes cleavage of a GT dinucleotide from each 3' vDNA terminus. All right, we're cleaving at 3'. And then what bond are we cleaving at 3'? Okay, so let me see if we have the marker here. All right, so if we're cleaving at 3', okay, I'm just going to make up a DNA segment here. So let's say we have like G, we have T, C, all right, and then we have GT. So we have G and then T here. All right, and this is the 5' here. This is the 3' here, 3' right here. Okay, so if we're cleaving at here, that is not cleaving the dinucleotide. If we cleave here, we're going to leave T and we're going to leave this GTCG. We don't want that. We want to cleave right here. If we cleave right here, we're going to cleave off that GT dinucleotide. So what bond is here? What bond is between C and G? Okay, there's a phosphate bond here and it's PO. Okay, I'm going to show you guys how, I'm not going to draw it out, but I'll show you guys how this looks like. All right, so DNA molecular structure. Okay, I'll show you guys where we're cleaving, all that stuff. All right, let's use this one. This one's good. Okay, all right, you should know how DNA nucleotides are incorporated into DNA, the host cell DNA, all this stuff. Okay, how are these nucleotides added to a growing DNA strand? And not no DNA polymerase, but molecularly, the molecular way of how DNA strands are added into this growing DNA strand. Well, it's simple. Okay, pretend this here doesn't exist. All right, so we're gonna pretend this isn't here. All right, we're gonna have an OH here. All right, that's the structure of the ribose sugar. You should know the structure of the ribose sugar. And I could see this is 1 prime, first prime, second prime carbon here, third prime. And the second prime carbon does not have an OH, so that should tell you what nucleotide we have here. But anyways, this O here is going to be a nucleophile and attack a phosphate group. All right, it's going to attack a phosphate group. And that phosphate group is going to hold the whole entire nucleotide. I'll put N here for nucleotide. All right, this is going to go attack that P. It's going to grab this whole entire nucleotide by doing that. That is the mechanism for this. The reason why it goes and attacks that phosphate is because these oxygens on this phosphate given a partial negative charge. All right, we have 1, 2, 3 oxygens, very, very partial negative charge on that phosphate. And because we have 1 partial negative charge, 2 partial negative charge, 3 partial negative charge, this phosphate is going to get a partial positive charge. And since this O is already, partially negative, that reaction here, this is very, very favorable, very, very likely to happen. So that's what happens here. All right. And because of that, all right, after that mechanism, we have an O and then a P here. Okay. And so we're going to cleave this bond here. So we get back that OH here in case we want to add another nucleotide. All right, I hope that makes sense. Comment down below if that does not make sense. I'm always here to help you guys. So I'm going to go with this one. Let's see if it's correct. What the heck? Oh, I got to put the review on. All right, let's see if it's correct. Bam. And there's the reasoning why. See how easy it is, guys? You guys overcomplicate stuff. All right, it's not that hard. MCAT is easy. I'll always say it and I'll always stick by it. The MCAT is easy. All right, I know you guys are probably hearing me in like, oh, no way, Eric. I hate this test. Okay, I hated the test too, but once you get the test on your side, it's a lot easier. All right, a viral DNA sequence encoding a protein is inserted into a host genome by integrase. The protein is translated from the hypothetical mRNA sequence shown. Based on the passage, the segment of the original viral genome that encoded this protein had what nucleotide sequence? All right, common MCAT trap here. All right, they're always going to try to trick you with the whether something's RNA, DNA, cDNA, reverse transcriptase, going from this to this to viral. They're always going to try to trick you with that. All right, so you guys have to get this down. And it's always important to hang on to every word in the question. All right, every single word in that question is very, very important, guys. Because if you do that, then you won't fall for these MCAT tricks. All right, so if I hang on to every word, all right, based on the passage, the segment of the original viral genome that encoded this protein had what nucleotide sequence? All right, look how they're trying to trick you. All right, if you recognize these traps, your score is going to go up by a lot. All right, they start off by saying a viral DNA sequence encoding a protein, and then they say, hey, but what's the original one? DNA is not the original genomic information of a virus. Okay, especially HIV. There are some DNA viruses, but that's out of the scope of the MCAT. All right. HIV starts off as RNA, all right, viral RNA, and then it becomes DNA, all right, and then this becomes, I'll say this is viral DNA, and then it becomes the mRNA, and then you should know it becomes protein, all right. The original is this guy. The original is not this guy, okay. The original is this guy. So anything that has a T in it, we know that it's wrong because that is DNA. We're looking for RNA. So I can eliminate that right away. So let's see what we can eliminate. T, B, we can eliminate. All right. C, we can eliminate. It's either A or D. Now, since we're going from this to this and then back to RNA, this viral RNA and this mRNA are the same sequence. Okay, think about it. If you can't really understand that, just draw it out. Let's say this mRNA sequence is, what do they give us here? GGC. GGC. And then the viral DNA would be what? CCG. And then the RNA from this one would be what? GGC. Okay, this one and this one are the same exact things. They try to trick you with that, but silly rabbit, tricks are for kids. Okay, I like saying that. So answer is the same one here, and that's the same thing. Is this correct? Bam! You already know how we do this. Let's keep going. Okay, let's see what else we got here. Ooh, we got some words here. All right. Which experiment would best provide data to support the mechanism by which an ODN inhibits ion activity? Hang on to the words, guys. Hang on to the words, okay? They're asking me what experiment would best provide data to support the mechanism by which an ODN inhibits ion. They're not asking me which experiment would best provide proof that ODN inhibits ion. I'm going to say it again. They're asking me, hey, what data shows and proves the mechanism is correct? They're not asking me and saying, hey, which experiment shows that ODN works? They're just asking me for the mechanism. And what is the mechanism? They mentioned to us competitive inhibition. All right. So all I got to do is see which one supports competitive inhibition. It's that simple. Go back to your content review. You should know this. All right. And I see constant velocity, concentrations increasing. So you should know, I'm going to do this before I even get to the question. But if you guys remember from competitive inhibitors, what do competitive inhibitors do? Okay, comp X up. That's my mnemonic. So comp X up. All right, so that's going to be equal to X, which is the Km. All right. And then we have up. So the Km is increasing. The Vmax is staying the same. And the enzyme concentration is going to be constant. All right. Why is the enzyme concentration constant? Well, that follows Michaelis Menton's, and also it makes things easier. Okay, we want to see, is this competitive inhibition? All right. If we have the enzyme concentration increasing and decreasing, that's going to make everything a mess. All we want to see is, hey, does this inhibitor bind to the active site? And can we overcome this inhibitor by increasing substrate concentration? That's all competitive inhibition is, okay? That's what we do, all right? And if you want to know more about it, if you're still a little confused, all right, think of like the Michaelis Menton plot here, all right? What do we have here? We have Vmax, okay, and then we have the Km here. All right, and then this is the substrate concentration. All right, what's happening here? We're increasing the substrate concentration. And we're looking to see, hey, how does this line change with respect to a competitive inhibitor? If we put a competitive inhibitor here, all right, and you could also do this with the Lineweaver-Burke plot if that's more easier for you guys. But if we put a competitive inhibitor here, okay, how is this going to change? Well, the Vmax will stay the same. So I'm going to do it as like dots here. It's going to stay the same. And the Km will increase, so it's going to look more like this. Okay, Km has increased, affinity decreased. All right, but anyways, that's how it is, guys. So I'm just going to look for an answer choice that follows this. All right, so let's see here. Keep in is the enzyme, okay, integrase enzyme. Keep in concentration constant, I like that, and measure the initial velocity of the reaction at increasing viral DNA concentrations. Okay, viral DNA is the substrate. That's the substrate here. And we're increasing the substrates in the presence and absence of the ODN, which is the inhibitor. Awesome answer. Okay, I really like that answer because we have the absence and presence of the inhibitor. All right, simple. Is this competitive inhibition? Let's see with it and let's see without the inhibitor. Okay, very good. Keep viral DNA, no. We want to have the enzyme concentration constant. Let's see. Keep ODN and integrase concentration constant and measure. Again, we just want to have the enzyme concentration constant. If we have the substrate concentration constant, that's not going to tell us much. Okay, we want to see if we increase the substrate concentration, is that going to overcome the inhibitor? All right, that's classic competitive inhibition. If you guys don't understand, make sure to comment down below. I'll explain it further. Or join the group. Join the group and tag me in a question, okay? So let's see if this is correct. I'm pretty confident in my answer choice. Always confidence when I take the MCAT. Bam, that is correct. Let's keep going. Which amino acid substitution for the conserved residue at position 64 is least likely to affect the enzymatic function of N? Let's look at 64. Okay, it's a D. It's an aspartate, negatively charged. Least likely to affect it is something that else is negatively charged. What's negatively charged here? Glutamate. Bam. All right. An inactive tetramer of integrase is expected to have approximately what molecular weight? Well, they told us that integrase is 288 residues. Okay, protein composed of 3 domains. Remember, this is how much it weighs in total. All right, for the monomer. The domains are just part of the monomer. That's just how it is. All right. And so if it's a tetramer, we can simply just do 288 times. I mean, since these are pretty far apart, you know, like this is 64 and this is 128, I could just do 288 times 4. And that's going to give me, like, let's say this is 300. That's going to give me like 1200. 1,200, 1,200. Okay, I could do that. And I would just choose D. Or I could just simply do the long way, which is the correct way, and think, all right, 288 times 110. The reason why I'm multiplying by 110 is because we have 288 residues. Okay, I'll put an R here. Each residue weighs 110. So in total, the weight is, all right, let's see. This is, I'll make this like, fuck it, I'll do it in a calculator here. I'm too lazy. Okay. It's going to be D. So 288 times 110 is 31,680. 31,680 times 4 because we have a tetramer. That's going to be 126,720. Obviously, you guys could do the mental math and just round. But for the sake of this video, this is closest to D. Yeah, go with the way I just showed. Don't go with the 288 times 4 because that could be wrong sometimes. And that's correct. Let's keep going. To determine if a small molecule acts like a Ledgen with respect to N, a researcher plans to incubate purified N both with and without the small molecule, and then perform a Western blot to detect N in each sample. All right, that's cool. Now, N will bind, Ledgen's going to bind and make it an inactive tetramer. Okay, when Ledgen binds, all right, it shifts the oligomerization equilibrium towards an inactive tetramer. All right, so we need it to be a tetramer. All right, we need that tetramer form. If we do denaturing, are we going to have the tetramer form? No. We're going to break up those bonds and we're going to disrupt it. Okay. If we have reducing, are we going to have a tetramer? No, we're not. Okay, we're going to have monomers. We're going to break those. We're going to reduce those disulfide bonds and break the 4 tetramer into single monomers. Okay, remember, we want a tetramer because that's how Ledgen binds to it. Native makes sense here. Okay, if it's native, we're going to have that tetramer there and we can see, hey, does Ledgen bind or does Ledgen not bind? If we have monomers, Ledgen's not going to bind. All right, so native 3 only. Bam. All right, and there's the explanation. And that's it. All right, comment down below, guys. Make sure you guys join this because I will be charging money. Okay, I will be charging you guys because I want to keep this group, you know, of high quality pre-meds and people that are really want to score well in the MCAT. All right, so hop on this quick before I close it down. All right, comment down below if you guys have any questions. I'll see you guys in the next video.